Every time you type a message to ChatGPT, something extraordinary happens behind the screen. The model reads your words, and in about 200 milliseconds, it performs roughly 200 billion mathematical operations to produce a single response. 200 billion! That sounds impossibly complex. But here's the remarkable thing. Every single one of those operations comes down to just 4 ideas from mathematics. 4 ideas that a first-year college student could understand. And today, we're going to see all of them. These 4 ideas are the mathematical pillars of modern AI. The first is linear algebra, the mathematics of vectors and matrices. This is how an AI represents everything it knows, words, images, sounds, all as lists of numbers. The second is optimization, specifically gradient descent. This is how an AI learns from its mistakes. Imagine a ball rolling downhill on a vast landscape, always seeking the lowest valley. That's gradient descent. The third is probability. This is how an AI deals with uncertainty. When ChatGPT chooses its next word, it's not picking the one right answer. It's weighing thousands of possibilities. And the fourth is information theory, the mathematics of prediction and surprise. This is the framework that measures how good the AI's predictions actually are. These 4 pillars, vectors, gradients, probability, and information, are all you need to understand the mathematical engine behind every language model on Earth. Let's explore each one. Let's start with the most fundamental idea. Everything is a number. A photograph is just a grid of pixels, and each pixel is 3 numbers, red, green, and blue. Stack all those numbers into a single list, and you get a vector, a point in a very high-dimensional space. Words work the same way. In a language model, every word has been converted into a vector, a list of, say, 768 numbers that encode its meaning. And here's where it gets magical. When words become vectors, their relationships become geometry. King minus man plus woman equals queen. That's not poetry, it's vector arithmetic. The direction from man to king, royalty, is the same direction from woman to queen. But a language model doesn't just store single words, it combines them. When you write a sentence, the model multiplies your word vectors by enormous matrices, transformations that rotate, stretch, and project meaning through space. This is the heart of linear algebra in AI. Matrices transform meaning. Representing the world as numbers is powerful, but it's not enough. An AI needs to learn, and learning mathematically means finding the right numbers. Imagine a function, a landscape, where every point represents a different set of numbers the model could use, and the height of the landscape tells you how wrong those numbers are. The goal of learning is simple. Find the lowest point on this landscape. Go downhill. The algorithm that does this is called gradient descent. The gradient is just a direction, the direction of steepest descent. Flip it, and you get the fastest way downhill. Step by step, the algorithm adjusts the model's numbers, each time making the predictions a little less wrong, until eventually the model sits in a valley, a set of numbers that makes good predictions. Every AI model you've ever used was trained this way. Billions of parameters, adjusted one gradient step at a time. GPT-4 did this for months on thousands of computers. The math is simple. The scale is staggering. Now, the model has learned good numbers, but how does it actually generate text? Here's a crucial insight. A language model doesn't pick the next word. It assigns a probability to every possible next word. The operation that turns raw numbers into probabilities is called Softmax. It takes the model's internal scores, called logits, and transforms them into a probability distribution that sums to exactly 1. And here's the part that makes ChatGPT creative. There's a single parameter called temperature that controls how the model chooses. At low temperature, the model becomes conservative, almost always picking the most likely word. At high temperature, the distribution flattens. The model becomes more creative, more surprising, occasionally even incoherent. Every time you adjust that temperature slider in ChatGPT's settings, you're directly manipulating this equation. The math is that close to the surface. There's one more piece of the puzzle. The model can now represent data as vectors, learn through gradient descent, and output probabilities over words. But how do we measure whether those probabilities are any good? This is where information theory enters the picture, a branch of mathematics invented by Claude Shannon in 1948, decades before anyone dreamed of large language models. Shannon's key idea was that information is the opposite of predictability. If I tell you the sun will rise tomorrow, that's no surprise. Almost zero information. But if I tell you it's going to snow in July in Tokyo, that's deeply surprising. High information. The mathematical formula for surprise is negative log probability, and the average surprise across all predictions is called cross-entropy. This is the exact loss function that every large language model uses during training. When you see a training loss of, say, 2.3 comma, it means the model is, on average, as uncertain as choosing uniformly from about 10 words. As the model trains, as gradient descent finds better and better parameters, cross-entropy drops and the model's predictions get sharper and more accurate. The four pillars work together in a single loop. Now let's see all four pillars working together in the architecture that changed everything, the transformer. When you type a sentence, each word becomes a vector. That's linear algebra. Then comes the key innovation, attention. The model asks for each word, which other words in the sentence should I pay attention to? Attention is just 3 matrix multiplications and a softmax. Queries, keys, and values, names borrowed from database lookups, combine to let the model understand context. After attention, the result passes through a simple neural network, applying the universal approximation theorem. And finally, Softmax converts the output into probabilities over the entire vocabulary. The model compares its prediction to what actually came next. That's cross-entropy loss. Then it sends the error backward. That's backpropagation. And it adjusts all its parameters. That's gradient descent. One cycle, 4 pillars. That's the complete mathematical story of how a language model processes a single word. Repeat this billions of times and you get ChatGPT. In this series, The Math Behind AI, we'll take each of these ideas and explore them in depth. We'll watch gradient descent navigate a lost landscape in 3 dimensions. We'll see why king minus man plus woman equals queen, and what that tells us about how AI understands language. We'll animate the attention mechanism, the single equation that powers ChatGPT, Claude, and Gemini. And in the finale, we'll put every piece together into one unified picture of the transformer. The math behind AI is not as hard as you think. It's beautiful, it's visual, and it's waiting for you. Subscribe and turn on notifications so you don't miss an episode. I'll see you in episode 1.